Swayam Prabha. Digital India. Educated India.
In this class, we will sort of revise and wrap up what all we have been doing in random vibration. We'll go through what all we did, some of them at least, and then move to the complete use of this results of random vibrations for determining the tolerance of a human being for the vibrations that exist in a car. Maybe you have already done a course on ergonomics. I'm sure that you know human factors, vibration, what can be tolerated and so on. Okay, so we will not go into those details as it is covered in another course. But we will understand this random vibration a bit more and see how we actually calculate, or what is that calculations that we do in order that we determine the levels that the human beings can tolerate. So we'll go through this, the whole of these things in one go. So we were looking at what is called as an observation. So in any in a probability sense, observation is an experiment, and the result of this observation is the outcome. In our case, we are looking at the roughness of the road, as we had seen. The set of all possible outcomes is what we called as sample space. So a subset of the sample space is an event. We explained it with simple example, and then the function or a map from an event to the real line is what we call as a random variable. So there's an event, there is a mapping to the real line, which is called as a random variable, and the map from this random variable to a probability measure can be done, or we can directly give this probability measure to the event. Okay, so this in a nutshell are the definitions that we need to know. We already saw that the random process is a family of random variables. Remember that we did this in the case of the roughness of the road, okay, as a random variable. So we said that we can take a number of measurements. So this family of measurements, okay, is now going to be used, and we can call this as the ensemble. Remember that the random variables have two indices. I put one in the bracket. In other words, this r can vary from 1, 2, 3, 4 and so on, and s is this distance, s is the distance, and this indices 1 of s, then zeta 2 of s and so on, are the independent realizations, as they are called, okay, or sample functions. Okay, so we have a number of such sample functions, maybe yes, and that we can call as zeta s and so on. So all these things, these roughnesses, form what we call as the ensemble of roughness values. Okay. Now there are two ways in which we are going to look at this. We can look at it at a particular value of Sn. Of course, this Sn can be, or S can be replaced by time, okay, and you can define the whole thing in terms of time. Note that we can look at this at S1 and look at another one S2 and so on. So we have now at S1 a number of what are called as random variables, okay, or the measurements that we do at S1, and we do similar measurements at S2 and so on. Now this one, for example, I can say zeta 1 or zeta 2, zeta 3 and so on has a probability density function, the most common amongst them being a Gaussian or a normal distribution. The Gaussian or the normal distribution function all of you know, and that is the Gaussian or the normal distribution function. Note that the difference between the probability density function and the distribution function, probability distribution comes out of integration of this probability density function, or the probability density function comes from the differentiation of the probability distribution function. So, for example, if I have to calculate the probability of this zeta, what is the probability that zeta is between a and b? What I need to do is to just integrate this between the limits a and b. Okay, p zeta gives the probability density function, and if that is integrated, you get what is the probability that this variable is between a and b. We are also interested in joint probability, okay, of two variables x1, x2, s1, s2 and so on. So, the joint probability is given by a Gaussian joint normal distribution function. Okay, joint probability between two variables x and y is that, look at that closely, probability that x lies between, or x of k lies between x and x plus delta x, and y lies in a range. Okay. So, in other words, it is the second derivative, or px comma y can be written as dou by dou I of dou p by dou x, or dou squared p by dou x dou y, where p is the probability distribution function. The joint probability can be written as shown here, and rho is what is called as correlation. We will see that in a minute. We talk about, when we talk about this ensemble, okay, we talk about what are called as expectations. Okay, expectations. So, in other words, it is the ensemble average is written in terms of expectation. Note that from a sheer definition point of view, there is a difference between the time averaging and the averaging across, or averaging of the whole ensemble. Okay, time averaging simply means that I am averaging across here. Okay, so expected value, or in other words, ensemble gives us what is called as the ensemble mean or ensemble average, and that is given by, okay, this we had seen it a couple of classes back, that it's given by mean is equal to the value zeta 1 into multiplied by the probability into d zeta. Okay. Now, remember that we had seen, so the key factor here is this equation, which gives you the expected value of, say, a function y is given by the expected value of y, okay, it's a function of x, or y is equal to g of s, a function of s, is given by g of alpha, p of alpha into d alpha. So, now I can replace g of alpha by any function. Okay. So, I can replace that. For example, if I am looking at the expected value of the what's called as the variance, then we can determine the expected value of the variance by substituting that difference zeta s1 minus the mean, okay, that can be substituted, that squared can be substituted instead of g, and calculate what is called as the variance. So, expected value of what is in this bracket, okay, that square of this term, okay, is called as the variance. You can operate the integral as you know it, you can substitute it, expand it, and that's the right hand side is what you get. Let's now, so the two important parameters, the first two important parameters are what are called as the mean and the variance. Okay, they belong to one set, say calculated at S1 or calculated at S2 and so on. So when I say it is mean or the expected value, it is across this line, vertical line. Okay. So if I talk about horizontal line, though it's distance, I would talk about time averages. Okay. Loosely talking, it's a time average. So average can be taken along the vertical line, or the average can be taken along the horizontal line. So those are the two things. The first is respect to one variable S1. You can then look at how two guys who are separated by a distance, say tau or time, okay, how they are related. There are two things or two definitions which now become or characterizes this connection between the two random, I shouldn't call two random variable, but random variable at S1 and S2, okay, because we have to be very careful in using these terms. This whole thing is one random process. Please note that this whole thing is one random process. The road is characterized as one random process. Okay, so I can say in that way this is not a different random process. It belongs to the same random process, and so they are the random variable. For example, if I look at the acceleration levels in the seat, okay, then I can call that as another random process. As we go along in these roads, what is the acceleration level at the seat if I calculate, okay, that is called as another random process. So I have another set of these values there as well. Then I will combine both. We will see that a bit later. So here we are looking at the same random process. So autocorrelation is the connection between those measurements that are done at S1 and the measurements that are done at S2. So that is the expected value, okay, it's the expected value of zeta 1, zeta 2. So you can see what is that, that definition is there. Okay, zeta 1, zeta 2, we are now replacing zeta 1, zeta 2 instead of g, and so the probability, now we see that there is a joint probability of zeta 1, zeta 2 multiplied by, okay, d zeta 1, d zeta 2. So the same thing,
In computing autocorrelation, why are you not subtracting the mean of?
Yeah, that's the second one is auto covariance. There's a there's a mistake there. It's actually auto. Then we have what is called as variance, okay, auto covariance. So that is subtracting the mean, and I think there's a small mistake in that, as it's not cross correlation, okay. It is again the auto covariance between the two. So the second line, that's the one. Okay. Now we can actually calculate what is called as so what is the difference between the two? The difference between this, the same as the difference between a mean and the variance. One talks about how much the variable is connected, okay. The other talks about how much the distance away from the mean, okay, how is that connected. So both of them, you look at one without mean and one with mean. Usually in most of these processes, we would make sure that the mean value, that is by adjusting the measurement that has been taken, we can make the mean value to be 0, in which case both these things would become 0, or in other words that m would become 0. Okay, so that is so the second one is actually the auto covariance. So that not cross correlation, auto covariance, and auto correlation and auto covariance is given by these two equations. Okay, we define what is called as a correlation coefficient. What's the connection? Why are we doing this? What is the relationship between the two? Once we finish this, once we finish a few more definition, we will look at what this actually means. Okay, so I define another one. I just normalize the variance. Okay, this auto covariance by means of the mean and I get what is called as the correlation coefficient. We'll come back to this correlation coefficient in a minute. Let's look at, we will now narrow down this process. Now, if it so happens, now look at this. I'm defining S1 and S2. If it so happens that the statistics, what we are defining, okay, does not depend on the particular value of S1 and S2, but depends only on, say for example, the difference in distance, or in other words time, okay, depends only on the time, okay, then we call this process as a stationary process. So the stationary process in fact can be classified into weakly stationary processes, or we can call them as strongly stationary, okay. So but we will not go into that detail, because then it depends upon whether all of them, all the statistical measures, or in other words all the moments, higher order moments, all of them, they are the same, okay, or they do not depend upon where I put this, my line doesn't depend upon where I put the line, but depends only upon the separating distance or separating time, okay, all the higher order moments, okay, that is very strongly stationary. If the first two moments depend upon this time tau, then we call this as a weakly stationary process, okay. We will just go to ergodic, then we will understand this whole thing, what we are talking about. Please note again, I am looking at it like this, the vertical segment, okay. So it is independent of time. In other words, that vertical segment, if I take and determine and do all my expected values and so on, or I take this vertical segment, they are the same, or I take two other vertical segments and then separated by that same distance tau, then all the statistical parameters that I calculate, they are the same, okay. So this distance doesn't come into picture, and that is what we call as a stationary process, okay. As far as we are concerned, we are interested in the first two, and so that's the first definition of stationary process. But a more interesting process, because of the limitations and other things, is called as an ergodic process. It's a special case of stationary process where one sample represents the whole of the random process. So here I have to go to a different roads and determine this, okay. So one sample determines the whole of this process. So I take a sample. If that sample determines all the statistics, then we call this, okay, as an ergodic process. More importantly, the ergodic process, we will see how it is. Whatever time averaging I do along this, the regular time averaging I do along this, that reduces to the ensemble or expected values. So the time averaging gives me the complete statistical parameter of the whole of the random process. Yeah.
So for that, should we have a long?
Yeah, we'll come to that. So one of the conditions, of course, is that the length of this sample, we say that the length of the sample has to be big. We'll come to that in a minute. What should be the length of the sample? So we call this, we already said that if the mean and the covariance, function are independent of time, and we also defined what is called as a strongly stationary process. So we said that if the ensemble averages are determined from the time averages of a single process, we said that's ergodic. Let's write down all the equations corresponding to that. What am I doing? I am only, okay, defining. You can also write this as an expected value, it doesn't matter. But when you write this in terms of time, the calculation becomes quite simple. So the first is the mean definition. Look at that, x tends to infinity, okay. So I integrate over a very large length. It's very important that the lengths are large, okay. So that is the mean across, that is horizontal side. So the mean, the variance, and the third, how look at how it reduces. So we will look at this from the probability density function will be Gaussian, and the third is what we called as, what's that? Autocorrelation. Okay, autocorrelation, and the fourth is the mean square value, and lastly we look at autocovariance. Okay, so what essentially has happened is that d psi 1, d zeta 1, d zeta 2, which we had put earlier, okay, that is now we have replaced it, okay, that time averaging, and so it becomes very simple. Now it's possible to get the estimate of all these things. We will not cover that in this course, what are called as estimators. We can do that estimators by looking at discrete values that are taken, okay, and then summing up the discrete values. We will not look at what are called estimators for these things. Okay, we will leave this as a continuous expression, and maybe we will cover that in one of the later courses. So these are a bunch of definitions which I'm sure you understand. If there's any questions, we'll take it. Okay. Now, what does these things mean? You know, what does autocorrelation mean? What does the autocovariance mean, and so on? It simply tells you how far, as a correlation, you know, as the term indicates, how far the signal that's happening at S1, okay, the road roughnesses, how far does it affect something that happens at S2? In other words, what is the memory of a signal? This is not only for a roughness, but it's also for any signal. So it looks at what is the memory of the signal. If this is white noise, which means that, say, we will talk about the spectrum or power spectral density, which is distributed throughout. In other words, it is purely a signal which is such that even the next guy, in other words, delta t, okay, t, if this happens at time t, what happens at t plus delta t, he also is not related to t. In other words, a white noise is where there's a stick standing at tau is equal to 0. Okay, you can, if you go and substitute tau is equal to 0 in the third expression, you would notice that that is nothing but, that's nothing but, if I substitute tau is equal to 0 in the third expression, this is nothing but the fourth one, r of zeta of 0, okay, it's nothing but the mean square value of this variable, okay, which means that there will just be a stick and it won't be connected at all. If, I mean, of course, this varies depending upon what are the frequency contents and so on. Okay. What is actually ergodicity? It's a very big question. It can't be covered in this course. There are what are called ergodic theorems and so on. We'll just follow a very simple method to just understand what this ergodicity is. So what we said is that we have a time or a space average. Let's stick to that word time because that's what is used in most textbooks. Okay, what we are saying is that the ensemble average, that is the expected value, is equal to the time average. How does this come about? Okay, let's look at this carefully. Now the expected value of the ensemble or the ensemble average given by that expected value, okay, we will substitute that, okay, expected value of, you know, in terms of what we had measured here, what we substituted here, this expression, switch the expectation. After all, expectation is the integration. Now you can shift it, okay, and ultimately you would see that, okay, when I substitute that, the ensemble average, okay, reduces to what is called as the line average or the time average, right? So what is important to understand is that for a stationary process, the ergodic process is also a stationary process. So this this expression, very simple expression, you can see that the simple expression where I just took the expected value inside shows that the ensemble average can be calculated in terms of the time average or in terms of the distance. Yes. Now, so these are the 5 things so which are important to us. That's what we had defined. Okay. Let's define what is called as a Fourier transform. We know that already what Fourier transform is. Note that 1 by 2 pi can be interchanged, it can be root of that and so on, okay, depending upon the textbook. So it is only a scaling quantity. So let us look at the 2 values, okay, the what is called as the Fourier transform and the inverse Fourier transform. Okay, these are well known. This comes from your Fourier series. Okay, you know that already. We will spend some more time in one of the later courses on all these things. So we define what is called as the power spectral density. Ultimately, we come to a quantity which is called power spectral. This is the 6th, right? 6th important quantity. Look at mean, variance, autocorrelation, autocovariance, correlation coefficient, which is nothing but normalized by means of the variance, a square of the variance, which is this, okay? And then we come to what is called as the power spectral density. Power spectral density is defined as the Fourier transform of the autocorrelation function. So Fourier, in other words, what is that we are trying to do? We are moving from the time domain to the frequency domain. Okay, we are moving from the time domain to the frequency domain. The autocorrelation function is in terms of time domain, and now we are taking the Fourier transform of it. So we have now moved to the frequency domain, right? So these are the 2, the Fourier transform and the inverse Fourier transform. I do an inverse Fourier transform of the power spectral density. We get what is called as the autocorrelation function. Okay. Substitute tau in that second expression, you would get the meaning of what is power spectral density. In order to understand what this power spectral density is, what is this power or spectral density as sometimes called, okay, spectrum as it is loosely called, okay, all this, what does this really mean? The expressions which I had written there, they are very straightforward, okay. They are just that the mean square value, okay, which is the autocorrelation at tau is equal to 0 is what's defined in the third line, that is this one. We had seen this before. If I now substitute tau is equal to 0 here, it becomes that the mean square value is nothing but S omega d omega. So in other words, the mean square value or the power, okay, is now determined in terms of the power spectral density. Now let's understand this more carefully. Let's for a moment take that second expression for granted. Let us say that I have a process, okay, where I send in an input and I get an output. Okay, let us say that the frequency response function of this process is h of j omega, and the impulse response of this is, say, h of t. Right? Let us consider that this process as a band pass filter, okay, with a narrow band. In other words, this is a filter which has the frequency response function in such a fashion that it allows only a small band of frequency to pass through. Going to filter off the rest of them. So if I now, in other words, let us say that centered around omega naught, okay, usually it's practiced to do both, so it is going to allow only a small narrow band. Okay. Now this pass band, this is what is passed. Okay, this narrow band of frequency is what is passed, okay, which I would also call as pass band if you do not understand this filter. Okay, let us now calculate the expected value of the square of this output. Okay, the expected value of the square of the output, in other words, mean square value of y. Usually the square of these any of these quantities, the electrical engineers are fond to call them as power. It comes from I squared r. So usually the square of a quantity is called as the power. Okay, so the mean square value, which we saw in the last slide, is now in other words, this slide we saw it there as the last equation. Now since this narrow band is only passed, this band pass is only a narrow band is passed. Okay, let's say that this is delta omega. That integral from minus infinity to plus infinity is now reduced, okay, reduced, because the rest of the places it is 0. So it becomes, this is the integral limits now. Okay, so that pass band is the power spectral density multiplied by d omega. Okay, and you can, as the band becomes smaller, you can understand that the power that is passed, okay, in a very small range is nothing but is given by the power spectral density. Sometimes, you know, some of the softwares which are used in mechanical engineering, they call that Sy omega into delta omega as auto power. Okay, so power spectral density, because the word density is used because when you multiply it by delta omega, so it gives you the power. So that's why the density term is added. Many of the NVH softwares, okay, you would see that they use the term auto power. In what they simply mean is that they multiply this with a band of delta omega. Okay, so that multiplication, in other words, what is inside the integral is what they call as auto power. Okay, so in other words, the spectral density or the spectrum gives you the energy content of the signal, and we are now looking at it in the frequency domain. The energy content at various frequencies is what is determined, okay, by the spectrum. Okay. One of the key factors, though we will not be deriving it completely in this course, take that as granted, is the relationship between what comes out here and what goes in. The relationship is given by the first equation. In other words, the power spectral density is a very key equation. The power spectral density of an output, okay, output determined from a linear time invariant system, okay, which is characterized by a frequency response function, okay, that is given by the square of the magnitude of this function multiplied by the input power spectral density. So in other words, if I have a vehicle, say for example we looked at a quadric car model, and we had looked at various frequency response functions at various places. Now if I want to say that I want to find out what is the power spectral density, say at the automobile, what we call as the sprung mass, say the base of the car, okay, the sprung mass, the floor of the car. Okay, if I want to find out that, we already know what is the frequency response function. We had written that. Okay, now that frequency response function, the magnitude square of the frequency response function, if I now take, note that it can be complex. So we're looking at the magnitude of the frequency response function. Square of that multiplied by the input power spectral density gives me the output power spectral density. So if I want to find out at the seat, I put one more, okay, what is the frequency response function between the road and the seat, I write it, and then I can find out what is the power spectral density at the seat location. Okay, that brings us to a very important thing, or the properties of these functions. The autocorrelation function, by the sheer definition, remember that there was a xt and xt minus tau. So from its sheer definition, okay, is such that it is a even function, or in other words, autocorrelation function of minus tau is equal to the function of tau, okay, from the sheer definition. So that's the first one. The second equation again comes from the definition. Go back and look at the definition. Okay, you would notice that in e power minus j omega t, substitute minus omega, okay, omega by minus omega. So you would notice that the power spectral density, in other words, what is this? This is nothing but the complex conjugate, okay, becomes the power spectral density of omega. In other words, the power spectral density is a real valued function. Okay, power spectral density is a real valued function, and that is what is, okay, important here, that the output power spectral density and the input power spectral density, both of them are related by the power spectral density, which is a real valued function. Okay, we can also look at cross correlation functions. These are the cross correlation functions, okay, between two different random processes. That's very important to understand. Okay, what we are looking at, this whole thing is a random process. Though we call this as one random variable and another random variable, they belong to the same. Okay, that's why we use the term here when we calculate, it's auto. Okay, so auto is what we used because it belongs to the same random processes. So we can connect two different, okay, the cross correlation between them. What happens when you give an input here? How is this correlated with another random process which is at a time? So in other words, if I have another random process, see, I have a random process and I have two random processes. Okay, the other random processes, let me call that as eta. It can be anything, you know, whatever. It can be maybe what happens at the seat location, okay, or something else. Now, the cross correlation is the connection, the statistical connection between, say, for example, that road input at S1, okay, to what happens, the statistical connection between that and at S1 plus, say, tau. Okay? Because of the fact that the distances do not now matter, because we are looking at something else, then so S has to be, okay, though we define the road in terms of distance, it's proper that we come back to time rather than stick to only distances. So please note that though I used it interchangeably, note that it's always better to look at that in terms of time. So we define what is called as a cross correlation, cross covariance, and cross spectral density. Okay, so cross spectral density. Note the difference between, okay, S, the power spectral density, eta to S zeta eta. Okay, so note that difference. The difference is at the same, we are looking at, when we look at the YY, you know, that is at this place what happens. Now there is a delay factor, okay, a tau, which connects the cross correlation factors. Okay, again through the definition we can see that the cross spectral density is a complex valued function. Obviously, it's a complex valued function. We also have to look at the phase, because we are looking at two different points, okay, and this is in the frequency domain, so we look at the phase as well. And the cross correlation function is neither odd or even, and again go back and put that in the definition, you would see that that's the expression you would see. One of the quantities, see, we saw the cross correlation coefficient, okay, or the correlation coefficient rather. Sorry, the correlation coefficient. One of the quantities that is in the time domain, okay, and one of the quantities of interest to us in the frequency domain, a corresponding in the quantity in the frequency domain is called as the coherence. Is called as the coherence. So all of you know what is a correlation coefficient. Okay, if the correlation coefficient, all of you know, varies from -1 to +1. Okay, rho is between -1 to +1. That's because we had normalized it by means of that variance. Okay, so it's simple probability. So which means that if there is a perfect correlation, then you know that you can plot that the two variables, and maybe all the points will fall in a straight line. And if there's a negative correlation, you would also know that, okay, when one is positive, the other is negative, and so on. Okay, so the negative correlation means that when something increases, the other factor decreases, and so on. So that is a correlation which we defined, okay, in the time domain. What is a correlation in the frequency domain? You should be able to now imagine time and frequency in a very, very similar fashion. The x-axis is time, now the x-axis becomes frequency. It doesn't matter, no, x-axis just becomes frequency. Okay, so frequency domain, where we look at this whole thing in terms of that f after we do the Fourier transform. In fact, today there are techniques that are available in order to look at, say, fatigue life in frequency domain. So you do that in time domain, or you can do that in frequency domain. So coherence, which is extensively used to look at how, look at the input and the output connection in many of the experiments. Say, for example, you would do some experiments in the vehicle dynamics lab, in which case you would look at coherence all the time and look at how, whether output, what you measure, is pure noise, or whether it is correlated, English word, correlated with respect to the input. Okay, that you look at it in the frequency domain. If the coherence is not near 1, then, okay, if suppose it is, say, 0.9 to 1, then you know that there is a good coherence between what you gave, or in other words, what you are measuring is due to what you gave as an input. If there is no coherence, then you would see that what you are measuring is noise, it has nothing to do with what you have given as an input. So coherence is an important quantity, especially you will be using that in the experimental work. One of the quantities of interest is what is called as the mean square value of the acceleration. So why are we doing all these things? Okay, ultimately I measure or I calculate what is the power spectral density at the seat. Okay, we know that. Now we have defined quantities. We know the connection between power spectral density at the road, power spectral density at the seat. We know that everything is done. Now, okay, why am I doing this? What is it that I am doing this? What is it that I'm going to get out of it? One of the simplest thing you would notice is that the acceleration levels, okay, what you, say, for example, feel when you do a drilling or something where you are subjected to accelerations, are very important input of vibration to our body. Okay, in other words, our tolerance levels depend upon the mean square value of the acceleration. Okay, now what is the mean square value of an acceleration? Remember, y squared, the same thing, Okay, mean square value of this. Now instead of y, we say that it is the mean square value of the acceleration. We know that this is nothing but the integral of the power spectral density. This is exactly what we did in this problem. So power spectral density in a band omega 1 to omega 2. Okay. In other words, we have a central frequency like this, and we take this band from omega 1 to omega 2. Okay. This band omega 1 and omega 2 is called as an 1/3 octave band. It's called as an 1/3. There are 1/6 octave band and so on. 1/3 octave band. If the upper frequency or upper bound, this point, is given by root 2 1/3 of power of root 2, or the lower frequency is given by, as you see, divided by third cube root of 2 and so on. When you calculate that, that becomes 0.89 to 1.2, 1.12 omega naught. Octave has a very important parameter, and we'll see that. Okay, again, next goes on noise. Noise and vibrations. So the RMS acceleration is now calculated, okay, based on the power spectral density. This RMS acceleration is related to our ability to withstand vibrations. Okay. Now we have various, so I can calculate for various frequencies what is the RMS acceleration from that equation. Okay. So in other words, I can have a plot of frequency versus the versus the RMS acceleration. Yeah.
That expression, it gives you the RMS acceleration at the road level, right?
No. It doesn't matter. I am looking at it anywhere power spectral density. So you can take that it's a general expression. So we are talking about power spectral density at the seat. So yes.
S is SAA.
Okay, yes.
AA. You know, in any A we can take, right?
No. This expression here is now substituted in terms of the seat. Okay. If you want to call this as eta, you can call this S eta. Okay. So suppose this is the road input, okay, and this is the seat. Y is the seat output at the seat, and then if I calculate the power spectral density at the seat and call that as, say, S eta or S eta, whatever it is, okay, which is nothing but, remember that h squared value, right? So I'm talking about this value. So take it to the seat. Okay, that is what goes inside that integral. Okay, and take 1 minute. Let me explain this process. And take 1 omega. Okay, and then put that as a band and calculate 1/3 octave band at that value. So I get one value for a mid frequency of omega by integrating that value. That is the RMS acceleration. Okay, for a frequency, that frequency. So like that, I will have RMS acceleration at various frequencies.
So that would give you the RMS
Acceleration is a function of frequency.
Why is that the acceleration? It will still give you the root mean square value of your seat position.
Yes, root mean square value of the seat position. But note that I am calculating or I am measuring, what I am measuring as an output, okay, that power spectral density of the acceleration. Say for example, if I measure the power spectral density of this output, okay, is what I measure is yes. So if I can measure anything, I can measure whatever I want. Suppose I put an accelerometer. Usually what I do is to put an accelerometer and measure it. And so what I get out is the power spectral density of this acceleration measured from the accelerometer, and that is what I'm going to use. Okay, it doesn't matter. The simplest and the best method is to put only an accelerometer and measure it. Okay. Now that is the so this is called as the RMS acceleration, right? So usually you can put an accelerometer at the seat, you can put an accelerometer at the back, okay, and you can put an accelerometer at the floor and so on. Now, a lot of tests have been done from the point of view of human tolerance, human vibration tolerance, okay, and it has been found that there is a difference about the tolerance level of a human being, whether we are subjected to, say, a seat vertical acceleration or an horizontal acceleration. Also, I'm sure you have been, this has been done to you, and you talked about a very famous standard 2631, okay, in your earlier course on ergonomics, because that is what essentially the whole of ergonomics is all about, that standard 2631. It's a huge standard, we don't have time here to cover it, but nevertheless, once I know how to calculate that RMS acceleration, you have what are called as weightage factors, and these weightage factors are applied, which are different whether it is a vertical vibration or whether it's a horizontal vibration and so on. So with these weightage factors, we will understand what's the tolerable limit, whether we are going to be comfortable or not. Okay, we'll talk about that in the next class. Okay, the last of the topics that we need to cover, which we'll do in the next 10 minutes, is what is called as the road roughness. Of course, you had already seen what is power spectral density. You already saw that power spectral density is very important input to this whole problem, and that road roughness is actually the input. Remember that many of the equations you can either solve it in the frequency domain or in time domain, okay, but nevertheless, if I have to give the road as an input, as a power spectral density, it is in the spatial domain. In other words, when you go and measure what is called as road profile, okay, this would be in terms of distance x, and the actual power spectral density, okay, from which you can get the correlation, autocorrelation and so on, is actually measured in terms of time. So we have to have a relationship between the spatial frequency and the temporal frequency. In other words, when the velocity of the vehicle is v, obviously the frequency with which the vehicle gets excited would be a function of v. So in other words, if omega is the what is called as, we'll call this as a spatial frequency, which means that this is expressed in terms of radians per meter, okay, and for the problems that you do, you require the same thing in terms of, say, radians per second. So I have to convert radians per meter, which is a road characteristics, that has to be converted into characteristics as an input into the system, into the vehicle, and that obviously comes from v, the velocity of the vehicle, which is expressed in meters per second. So obviously omega, which is radians per second, is given by capital omega spatial frequency multiplied by v. Okay, so this becomes, omega is radians per meter, meter per second, so this becomes radians per second. Okay, so this is the first thing that we need to know, understand, when we convert the spatial frequency or spatial power spectral density into a power spectral density which goes as an input. I don't want to call this as temporal and confuse you, just that as an input, when at power spectral density, when it goes inside all our calculations, then it should be in terms of the omega should be in terms of what is called as the temporal frequency, that is meters per second. Okay, now, so this is a very good, nice way of distinguishing between the road and the vehicle. So that brings us to the topic of how do you specify a road roughness. In other words, how do you characterize the road? There are a number of ways in which you can write down an equation for the power spectral density of the road. Okay, let me call that as the power spectral density of the road. The power spectral density of the road is written in terms of capital omega, which means that it is written in terms of radians per meter, is given by a characteristic power spectral density phi naught multiplied by omega naught by omega whole power w. The w actually indicates the waviness, and w varies from okay, of course you have the wavelength to be 2 pi by omega, obviously you know that, and w actually varies from 1.75 to 2.25. Practice is to put w is equal to 2. Omega naught specifies a characterized frequency, a standardized spatial frequency. Okay, it's a standardized spatial frequency. We will see in the next equation how we are going to characterize the standardized spatial frequency. This was one of the first equations that were written. The equations were further modified later, okay, and there is an ISO specified power spectral density of the road. So you want to calculate the power spectral density of in terms of the temporal frequencies radians per second. We will do some small manipulation to that. Now the ISO came up with a small modification to this, and they said that if you plot it in a log-log plot, then there are actually two different slopes in a log-log plot of the frequency versus the power spectral density. So they gave this, actually this is good to plot in the log-log plot because of the type of equation you have. So the equation that you get is something like this. And for omega greater than omega naught, the equation is equal to the same similar type. Only thing is that omega to the power w2. So in other words, there are two slopes, okay, and they are characterized by two equations or two w's, w1 and w2. W1 and W2. Now the good roads and the bad roads are characterized by these W1 and W2. So if you really look at that, for example, for a very good road, the standards are something like this. For a very good road, the range of this W1, W2 is less than 8, which means that 0 to 8, the geometric mean is 4, and this is called A class road. And for a B class road, which is a good road, this range is 8 to 32, okay, and that is the phi naught value, okay, and then C, which is an average road, values vary from 32 to 128 and so on. Okay, there is a poor road which is 128 to 552. That is 128 to 512, and so on. The usual practice is to have W1 to be 2 and W2 to be 1.5. So in other words, the lower bound for an average road, if you want to do an analysis, the lower bound for an average road, you replace this phi naught by 32. Okay, that gives you the lower bound. Okay, of course omega naught is 2 pi, okay, and phi naught is 32. And for a upper bound, you replace that phi naught by 128, okay, and put that here, right? So you can have for an average road, I can't give you one figure, okay, it varies from 32 into 1 by 2 pi omega whole power 2, and then again the same thing whole power 1.5 when omega naught changes. This is a very standard ISO standard, but people in recent times have issues with this. The issue is that when omega, the frequency, okay, if you really look at a graph, the graph would be something like that with respect to omega versus this phi. There have been issues with this equation. The issue with this equation is that when that omega, the omega value, when it goes as it tends towards 0, the perspective density now shoots up, okay, and goes to infinity. The variance reaches infinity at omega is equal to 0, when omega is equal to 0. So that gives us a very unrealistic value when you reach omega, okay, when you move omega to be closer to 0. In other words, this would start, this part, the error is very large, okay, because of that fact that as omega tends to 0, okay, this one tends to infinity. So in order to avoid this, in fact, just one statement is very important, that essentially what is that you do? You put down an equation. So if you want to, like for example our road, if you really want to model your vehicle in this road, then you have to do a profile measurement, and then you have to fit a curve, okay, which is given by an equation which you are going to write down or which you have written down. So it's very important that you identify a road with an equation of this form, or an equation which we are going to put down because of this difficulty. Okay, there are a number of issues. For example, this gives what's called white noise, but the roads are colored noise, where there are a number of parameters. We are not going to cover all that in this course, but there will be a course on NVH if any of you want to take it, maybe next semester. That's after this, 2 semesters from hence, this in the January session, where the first part of the course will cover a lot more on random vibration as well as on signal processing, and there we will be covering more detailed analysis of the road, as well as how, what is white noise, what is colored noise, what is shape filter, what is shape filter which converts white noise into colored noise. All those things will be covered there. So the only thing I'm going to write down before I close this topic is that there's been changes in the way the perspective density is written because of this difficulty that omega makes this omega, as omega tends to 0, the perspective density goes to infinity. So in order to avoid that, there have been other, this kind of unrealistic behavior is avoided by using other types of equations or that's one type of equation. The other type of equation that's written and so on. So these are other types of equations which gives you a more realistic picture of the actual road measurements, especially as you move towards omega to be small, you get a much better picture of this. And of course, when you want to convert it into omega, substituting for V and so on, so you would notice that we can write down V phi naught into omega naught. Say for example, if W is equal to 2, you can write down that as the equation. There are a lot more issues in random vibration. Because of lack of time and this being the last class, I do not want to go into further details. People who are interested in some more details can slightly more information. You can look at Gillespie. Others, if you want more details on shape filter, white noise, colored noise, can look at a paper by Sheelan in the journal Sadhana. Okay, we'll stop here, and this course will end with this, and we will continue that in the next course. Okay, thank you.